So we are actually recycling our water. It's something good. Okay? So it's one of the things we're going to have to do more and more as we go into these drought time frames and global climate change and all these other things, regardless of whether I believe it or not. We're going to have to do something because we have too many people and too little water. And it's something outside California is really desperately looking at. So here's the nice USGS water cycle. There again, we have evaporation, condensation, rainfall, back in, overland, and some in the ground. That's our basic water cycle. Okay? Any questions with that? Pretty simple, been taught it your whole life, not a problem. Okay, meteorology. One of the things we have to keep in the back of our mind is climates do change. Okay? Now, why they change, we can argue that another time, but they have changed over the 4.6 billion years that our planet's been around. 15,000 years ago, Chicago had a mile-thick sheet of ice on top of it. Okay? It's not there today. Okay? Things warm up, things cool down. Yes?
Could you define the difference between climate and weather? Can everyone hear?
Yep, I'll repeat it.
I think that a lot of people get confused.
Good point. Climate versus weather. Okay? Weather is what's happening today. Okay? What's happening today here versus what's happening in Chicago. Climate is that larger scale change that's happening over all of the United States or all over a region. So think of the weather as being the local data point, okay? Climate being the bigger picture stuff. The thing to keep in mind is our data sets for weather are pretty limited. Okay? The planet's been here 4.6 billion years, and we have weather data for a couple hundred years. Okay? Climate data we can see in the rock records, but there again, it can be changing, and there again, there's other issues with that. But we certainly know it's changed. Precipitation and snowfall. Snowfall is certainly one of the things we utilize here for rain capture or for drinking water. Capture it in the Sierras, bring it down through canals, San Francisco, and those places. Temperature plays a role. Other factors is where you're at, latitude and altitude. Certainly, higher in the mountains gets more snow. Down in the valley, of course, I was really hoping I was going to have snow a couple weeks ago in Orange County. We didn't quite get it. Just drop another 1,000 feet, we would have had it. So certainly when you look at California, we live in an area that gets 10 to 20 inches of rainfall. Okay? That's limiting, so that's why we have to do these other things. When I was going to school in Michigan, water was plentiful. Dig a hole 5 feet, you had water everywhere. Okay? Not a problem. They get 60 to 80 inches of rainfall a year. Population of a few million people, it's easy for water resources. Not the case in Southern California. The other thing we have to concern with in Southern California and anybody on the West Coast, so any of those from the East Coast or east of the Rockies, notice the humidity, right? It's one of the nice things about the West Coast, we don't have much humidity. Well, the rain shadow effect is part of that. As the Pacific Ocean gets evaporated, starts condensing, you got these clouds that are really heavy. Well, the heavy clouds can't lift up very high, so they have to hug the ground. They run into this big mountain sitting here. How do they get over it? They lighten their load. They rain, precipitate, snow. They get lighter, they rise, then they move over. Now, why we have the Mojave Desert is there's no rain or precipitation left in those clouds, so then it keeps on going. So that's one reason why in the coastal ranges of Oregon, Washington, and California, we have a lot of rainfall on one side of the mountains. We have very little on the other side. It's called the rain shadow effect, which has to do with groundwater, right? So if you're trying to look for groundwater, Mojave Desert out here, 600, 800, 1,000 feet to groundwater. This side, with a lot of rain, which is recharging the system, groundwaters tend to be very shallow. Okay? So there again, it's all playing back to one another. The other thing we have to talk about when we talk about our water cycle is surface water. Okay? Lakes, rivers, streams, wetlands, the ocean. These are all things we can see, we can touch. We understand these pretty good because we've waded in a lake. We know we've waded across the stream. Okay? These are things we can feel, touch, therefore they're pretty well understood. One of the ways we study streams, rivers, and lakes is using a graph. Okay? The graph is strictly time versus discharge, and in this case, it's elevation of the creek or lake or river. Okay? So certainly more water is moving through the LA River when the water is up to the top than if it's just a little tiny trickle going down the bottom. So we can track that by days and time. And so here we have what's called a hydrograph that actually plots per day what that flow was in there. Okay? When you have an unlined stream, unlike the rivers we have in Southern California, the water is obviously doing something at the bottom of that particular stream, that bed down there, that's what's called a riverbed or lake bed. There's something going on at the bottom. It's not concrete keeping the water up. So what we do is we look at this because you notice one of the things that's happening is how many have actually spent a lot of time outside California? Minnesota, Michigan, Iowa, any of those places? Do the streams and rivers there run year-round or only part of the time? Year-round. Year-round. How does that river run year-round if there's no rainfall?
Because it comes out of the ground.
Because it comes out of the ground. The groundwater is feeding those streams and rivers and lakes all the time. So it has a base flow. Here, on the other hand, are rivers and lakes, i.e. the Mojave River. Go out to the Mojave River, water's in it for about 4 minutes before it's gone. Okay? Okay? There, the water comes to the surface and immediately goes into the ground and goes down, which groundwater there is 800, 900 feet below it. Okay? So we have two different systems going on. We have ones where the streams are running all the time because groundwater is feeding it, which we'll talk about that in a second here, and other areas where it only runs occasionally when it rains, where it's actually feeding the groundwater system. And so we end up with what's called a gaining stream in the Midwest and back east versus a losing stream, which is what we have here in Southern California. Okay? Now, why is that important to groundwater? Well, one thing is if it's gaining, the groundwater is coming to the surface and running off very fast in those rivers and lakes. Here, the rivers and lakes are a source of water getting to the ground. Okay? And so those are things we have to concern ourselves with if we're going to look at the water budget and the water cycle. So now we get to groundwater. Groundwater there again is that thing we can't see below the ground. It resides in between the rocks and the sands and the silts and clays. It resides in the gravel, in the fractures of bedrocks and whatnot. There again, one of the things I've always tell my students is you can find groundwater anywhere in the world. Okay? The key is there enough there to do anything with, and is the water quality anything you can do anything with too? It's always there. It just may not be in quantities and quality that you can utilize it for. Okay? And so we're going to have to talk about that. So if you see here, we got some fractures here with some water in it, and over here we have some gravels and stuff, and it just basically makes up all the stuff that's in there. So remember, it's the water contained in the spaces of the soil and the rock. Less than 1% of all the water on Earth resides in the ground, but however, it's 40 times more abundant than that of what we can see at the surface. So some terms. We have the water table, saturated zone, and zone of aeration or unsaturated zone. So if we start at the surface, right, it's the easiest one to start. We're standing right here. If I could just see down below me, this would be the surface. As I go down in the geology of the rocks beneath me, there'll be an area where it doesn't have water in it. Okay, that's going to be the vadose zone, zone of unsaturation. It's going to be this area up here. When I dig down sooner or later, I'm going to get to a point where I'm going to encounter moisture and water. Where water takes up 100% of the space in between all this stuff, that spot, that elevation right there is called the water table. Everything below that makes up the aquifer. Okay? Now there's some complications to that because there's a capillary fringe on top of it and stuff, and the water has to get there, right? So there's always going to be some moisture in that vadose zone up above, but the water doesn't take up 100% of the pore spaces or the spaces in between things until you hit the water table. Okay, does that make sense? So if you look over here, here's my vadose zone or unsaturated zone. So there's going to be some water in here, but it's not going to take up 100% of the space. As soon as I hit this water table, which is the top of that, from here down, 100% of that area is taken up with water. Okay? Above it, it has air and water. Okay? The other thing that I tell my students is how do you know where the water table is at? Well, it's the level to which water will rise in an unlined borehole. Okay, now that doesn't make a damn thing sense to anyone in here. But think about going to your backyard and digging out a hole. If you dig out a hole and there's a pond at the bottom of it, okay, especially if you're in the Midwest, here it's a little bit different because remember, water tables are deep, but nonetheless, that would be the water table. Okay? There's some things we're going to have to talk about with that, but that's kind of a way to look at it. So what is an aquifer? Okay? Aquifer is that body of rock or soil that has 100% of its porosity, we'll talk about what porosity is here in a second, filled with water. Okay? Now what happens is we can have a couple different types. We can have unconfined and confined, and I got some illustrations here in a second. They're going to explain what those are. But an unconfined is typically, not always, but typically your first encounter with the water table. That water is being recharged. When it rains, water goes through that vadose zone right to the water table. That's going to be your unconfined system. There's nothing confined and put under pressure. We're going to talk about that here in a second as well. A confined aquifer is one that has something that's confining it. Think of something like a pipe or a garden hose. The water can't escape the hose until it gets out the end. So something's keeping the water inside that, and that's the hose. Okay, that can happen in geology as well. When we talk about aquitards and aquicludes, these are the rocks which are, water moves very slow through them. Those are the things that can keep water down at some depth or keep water up in some cases. Okay? So all rocks don't behave the same. And so we're going to have to talk about those a little bit. So the other thing we're going to have to talk about is faults. Okay? We live in Southern California. Now, there again, I told my wife, I moved her from Chicago out here and said, we're moving to California, and the first comment was, we're going to fall in the ocean. Okay? No, we're not. Okay? However, we do have earthquakes, and it was pretty surprising to my wife the first time we had an earthquake, and she jumped out of bed, and oh my God, we're all going to die. Okay? We're used to faults and earthquakes around here, but it is part of our life. They are also barriers and conduits to water. Okay? Some faults act as barriers. Water does not want to move across that fault very well. It might move with it, but it won't move across it. Some of the faults that we're looking at in the Mojave Desert, we're starting to see that they're actually acting in some ways as conduits for water. Okay? So not every fault acts the same, but they are something we have to concern ourselves with when we start talking about how groundwater moves when we can't see it. And here's a nice little picture of Orange County's system, and you can see all these little brown things in there. Those are clays. All the blue in there are the various aquifers or saturated soils within the subsurface. Okay? It shows it's pretty complex. It's not as easy as saying it's one big giant bathtub of sand. It's got other things in there that slow down water, speed up water, impact water chemistry, some don't. Yes?
What size area is that?
This is the ocean. This is Newport Beach, and this is just about where Cal State Disneyland's at. So it basically runs down the Santa Ana River. From Anaheim to the ocean, yeah, 20 miles. Yeah. Yeah?
This has nothing to do with your presentation, but it does with the general subject. You're mentioning faults.
Mm-hmm.
I belonged for many years to Earthquake Research Associates at Caltech.
Mm-hmm.
I know I live adjacent to Runkle Creek in CD Valley.
Okay.
Runkle
Don't know where
Creek
it's at, but.
has a dam above it, Runkle Dam. There is also Runkle Fault and many other faults. I would like to see in the later presentation, it's not mentioned here at all, not you, but later, as long as we're on this subject of fault, I would like to see that included, because that poses a huge danger of contamination from radiation and perchlorants below Runkle Fault, Runkle Creek, dam.
So your
And
question is about the effect of the fault along Runkle Canyon?
not just the effects of the fault, the effects of the water that is stored in Runkle,
Okay.
behind Runkle Dam. I'm very concerned.
Okay.
Good question.
Thank you.
Good question. Okay, continue on with my stuff. Continue on with my stuff. The hell with that. Okay. Okay, now, back to confined aquifers. Okay, now we talked about unconfined aquifers. So, if you think about, I got my land surface here where I'm standing, I dig down, I encounter the water. That water can get recharged when it rains, because it's, goes or irrigate my backyard, or septic tanks. Is anybody here live in Malibu? Do you realize everybody in Malibu sits on a septic tank? Everybody. Imagine that. It's been good for business, though. Okay. Now back to this. Okay, so that first one is unconfined. The other thing that unconfined aquifer can do is barometric pressure. Go back to that climate, meteorology, climate thing. As barometric pressures change, it can push down that unconfined aquifer or it can relax it. So it can go up and down just because barometric pressures change. Okay? It would really be important if we had hurricanes here, but it's okay. In Florida, it can go up and down quite a bit. And here it goes up and down quite a bit, a few inches maybe. Okay? A confined aquifer, on the other hand, is actually separated from the land surface. It's got that area of rock which is either less permeable or what we call impermeable. Now it turns out, technically, nothing's impermeable. Water will go through anything given enough time. Okay? Just does. Okay? Now, the time can be 10,000 years, 100,000 years, or whatnot, but sooner or later it'll find its way. Okay? So we have this, usually clay. Underneath that, we have another aquifer. So here, we have my unconfined aquifer seen here close to the land surface. Here's that zone of, say, clay. Below it, I have another saturated soil, maybe sand and gravel, filled with water. This clay, or this aquitard, is confining the water below it, so it's under pressure. Okay? And its pressure is dictated by how far back upland or uphill this water is being recharged into it. What's important about this is the question I get all the time by every student is artesian wells. How can I put a well in and have it flow out? Okay? Same thing happens with oil and gas. We've all seen the Beverly Hillbillies, right? Everything starts squirting out of the ground. Okay? Well, water can do that. However, it has to be under pressure. Okay? And the pressure, or that source of that pressure, has to be at a higher elevation than where the land elevation is where that water is coming out at. So you can see here, we put a little pipe in the ground, and water started squirting out, and it would squirt out at the same elevation as we have where a recharge started taking place. Now, it's a tough concept to get, and I understand that. Okay? The biggest idea you need to take away from here is there are two major types. Unconfined goes up and down at barometric pressure. Confined is under pressure, doesn't come up to the surface unless it has a hole or a mechanism to do that. Okay? And the other thing we can do is we can have little lenses, and this doesn't happen a lot around here, but certainly does in the Midwest where we have glacial materials, is we can have this little aquitard or aquiclude, whatever you want to call it. You can actually have water perched on top of it. So you can have almost a little lake sitting on top of this thing, drill through it, and actually have a dry zone. Okay? And so in glacial tills, thanks to the glaciers, we have a lot of this, which really wreaks havoc on contamination and water resources, because you can have a little aquifer up here, think you have lots of water, and all of a sudden you use it up real quick and realize it was a little tiny bathtub of water rather than a whole aquifer. So here, oops. Okay, so here's a better illustration of what I'm talking about here. Down here we have the bedrock. This should make the movie guys really happy that I'm walking all over the place. So, okay, so here we have our bedrock, or the bottom. Doesn't mean there's no water there, but in this particular illustration, I'm just trying to show this rock down here. Here we have some sand and gravel. Here's some clay, some fine grain unit, and whatnot. We have another sand and gravel and soil. So here's my Vado zone. Here's my unconfined aquifer. Water here can go up and down based upon rainfall, and it can go up and down based on barometric pressure. And you can see my well here, the water level in it is equal to the water table. Below here, I have a confined aquifer. This one's under pressure. Water's coming in from some distance away. When I put my well in there, the water level comes up to the level from which it's being pressurized. If it was artesian, it'd be off above the land surface. In this case, it just happens to be higher than this well next to it. So one of the fundamental things we do in hydrogeology is we want to put wells at different levels. Why? Because we want to see what the pressures are at different levels, because that gives me an idea of whether or not the water is wanting to go upward or downward vertically. Okay? Which is pretty important, right? If water wants to come up, okay? In fact, go back to the river, right? The river is gaining. Groundwater is wanting to come into it. Okay? So that's an area where, you know, for lack of a better word, that's a place that we wanted, that's an area we can tap for water. Water's coming into it versus where it's going out. The other thing that makes hydrogeology complex, and there again, you know, there's always those words you can't pronounce. Well, here's the ones I can't pronounce. It's like synonym. I can never pronounce that word either. Okay, we have isotropic, anisotropic, homogeneous, and heterogeneous. That's about as close as I can get to pronouncing those words. What it amounts to is, if you take a kid's sandbox, the material in that sandbox is uniform. Go down to the beach. All the grains in the beach are roughly the same size. So they pack together nicely, but they're all the same size. So the properties of that, which we're going to talk about in a second, are equal in all directions. Versus an area where it's heterogeneous, over here, where things may be oriented in different directions. Okay? A good example would be a fault. Okay? Let's say the fault is a barrier. Water's coming towards it, but all of a sudden it can't go any further. It adds complexity to the equation. Okay? If everything was like a nice little sand tank like I'm going to show you up here, I could teach anybody to do hydrogeology. Luckily for me, it's more complex than that. Okay? So that's why it takes a lot more information and a lot more details, because nothing is perfect as a sandbox. Very rarely do we get to do projects right on the beach. We end up doing them where we have sand and gravel over bedrock, and the bedrock's fractured, but it's fractured in this direction with a minor component this way. That means water can go both those directions. Well, which one's more important? Okay? So that really adds the complexity to it. But there are terms you're going to hear a lot if you read any of these documents. Not that I've read any of them, but I'm pretty sure you're going to see these 4 terms in there. The terms we associate with those properties are things like porosity and permeability. And porosity is the volume of water that can be held in that soil. Okay? The good example is, take my sand. Okay, I have 100 milliliters or 1 gallon of this sand. And I take 1 gallon of water and I start pulling the water in the dry sand until it fills up with water. Okay? What's going to happen is about 40% of my gallon of water will be filled into 1 gallon of the soil, because the porosity is about 40%, 35, 40, and whatnot. What's interesting is clay, which we always assume, you know, modeling clay and stuff, it's pretty tight. Water doesn't go through it. Its porosity is darn near that equal of sand. Okay? So they both can hold about the same amount of water. Okay? The problem is permeability. The ability for that soil to allow water to move through it. Okay? Clay has a very, very low permeability, okay, with a high porosity. Sand and gravel have a high porosity and a high permeability. Okay? That's why when we do production wells, we want to put them in sand and gravel, because we can get there's a lot of water there and we can get it out of the ground easy. Okay? Yes?
So you're saying that if a area is more permeable, then the water moves through it faster.
Easier.
Well,
Easier. And then we'll talk about we'll talk about speed here in a second. But it
what's
certainly
the
moves through it
difference
easier.
between being easier
Well,
and faster?
because what's driving it? Okay?
Pressure.
Take your bet. Well, there again, if you have no pressure, it'll move slower. If you have a lot of pressure, it'll move faster. It's like your bathtub, right? Bathtub is very permeable, very high porosity, right? It's a big open hole. But it can stay there, not moving. It doesn't move until you either add water to it or drain water out the bottom. Now, it's that slope, and we'll talk about that in a second, that's the driving mechanism, which is pressure. So if you have pressure on it, then it'll move quite rapidly. If you have no pressure on it, it doesn't move very fast. That make sense?
Well, yeah, the pressure, more pressure if the
More pressure, the
top
faster
of
it
the
moves.
area where, if you got a high area up here that allows water to move down into it, then the greater the pressure.
Yep. So if you're in the Rockies versus Kansas, a lot of pressure there.
Yeah.
Yeah. So, yes.
I'm sorry, cutting it.
Oh, so.
My question is, given that there's variability in permeability and porosity, are there basic numbers that describe these? I mean, you have multiple
You're ahead of me. I'll be there in a second.
Okay. It's like I was talking about for the San Susana field because they
Well, I don't know about that place because I can honestly say I'm completely ignorant of that place, to be honest with you. And not just saying that, but there's some references that I gave them, and I think it's one of the things that got lost, which has some tables in there on that, and I got some that's in here as well.
It's not just low, medium, high.
I agree. There's actual values. Now, the thing to keep in mind is geology is, I love fighting with engineers. I'm a geologist. Engineers like to have it down to, it is 13.2. Well, geology doesn't work that way. It's between 5 and 3,000. Okay? And the order of magnitude on these things are 2 to 3 orders of magnitude variability because every spot is different. Out here is going to be much different than it is in Orange County versus Mojave versus Minnesota versus India. Okay? But there are general numbers that you can use that give you at least within that bracket. What is exactly that site? There's investigation tools for that, and I'll talk about those as well. How do we determine exactly what is there? Okay, good. Okay, one of the things we talk about, and I'll skip through this pretty quickly, is we talk about sorting. It's one of those things, we're talking about grading and sorting. So when you look at the well logs and all the soils out there, and you're going to look at probably lots of soils, obviously, based upon that comment, is they're going to talk about things being poorly graded, well graded, poorly sorted, and well sorted. And you go, oh, what the hell does that mean? Okay? The easy thing to remember is grading. Okay? And you can remember grading because of me. Okay? I teach at Cal State Disneyland. Okay? A perfectly graded a class would be as I give I break the class up into equal number of F's, D's, C's, B's, and A's. In the university, that would be a well-graded class. Okay? However, I'm not good at well-grading classes. I'm a poorly grader. I give everyone C's. Okay? Just enough that I don't have to ever see them again, not enough that I get hit hard, okay? So a poorly graded class is one that has just C's. Well-graded has equal numbers of each of those different letters. Sorting is 180 degrees from that. If something is well-graded, it's poorly sorted. If it's poorly graded, it's well sorted. I always almost have to catch myself there. So think of grading and sorting just opposite. Okay, something's well graded, poorly sorted, poorly graded, well sorted. Because how can you get a well graded and a well sorted? You can't.
Well, how can you get something well graded? How something gets
Because think there again. Remember, grading is something that's well graded is equal distribution across all of it. I have gravels, sands, silts, and clays mixed together. Maybe a boulder in there. Something that is poorly graded is all sand. Okay? And where's a good example of that? Go to the beach. It's well sorted, but poorly graded because it's all one size. Okay? What's important about that, go back to the permeability numbers. Okay? If something is very permeable, you want it to be poorly graded, well sorted, like the beach. Okay? All roughly the same size. Fortunately, nature kicks us in there by putting some other fine stuff in there and some big stuff in there, like glacial material. It's a mixed bag of everything. I love talking about glaciers because it has sand, silt, gravel, clays, and boulders. When you mix it up, what happens is all these little spaces in here start getting plugged up with smaller and smaller stuff, making it less permeable for the water to move through it. You go to the beach, pour a bucket on the beach, goes right in, right? Take it in the backyard and dump it on. It may go in, but it goes in slower. So it's a good example of how we can have some of those things filling in those spaces. There again, just adding to the complexity and making things more heterogeneous rather than homogeneous. Now, fractures, it's very the same way. You can have fractures the size of this room. Great, right? Water's going to run right through this room. Problem is, if this fracture doesn't connect to anything, it's never going to go anywhere. Okay? So that's one of the problems with fractured bedrock is we can have lots of fractures, but if they're not connected, there's no way for that water to get from here to the one next door, regardless of how big they are. Okay? And they tend to have orientations to them, where they tend to fracture in one direction. But there's always these offshoots from it, so it makes it more complex. Okay? It doesn't mean we can't handle it. It's nothing we can't deal with. It just makes it more complex than a nice little bucket of sand that we might have.